Today we are privileged to have Dr. Srinivasan Rangarajan who is going to speak on the STEM lessons from Chandrayaan mission 3. Uh, uh, Dr. Srinivasan has done a PhD in physics from Mumbai University in the back year 1975, post which he was working with ISRO as a director from the year 1978 to 2000. That is a 22-year long stint. After his association with ISRO, he joined World Space as a senior VP Engineering Solutions from the year 2001 to 2009. Thank you.
Thank you very much, JanyuTech and the rest of the people. First is about the way I've titled this. I put in STEM. Obviously, this audience knows that is science, technology, engineering, mathematics. It's something which everyone talks about it. The Prime Minister talked about it from the ramparts of Red Fort the other day, saying the women are becoming more and more STEM oriented and so on. And we believe that STEM kind of learning is good for doing jobs in, say, things like space sector, aerospace and all that. But on the other hand, I believe that when I look at a satellite mission, space missions like Chandrayaan or today's Aditya L1 mission, which was a perfect book kind of a launch. And that particular, all these events always trigger in me the kind of things that our students can learn, the basic physics lessons or something in mathematics or something of technology, which with these realistic examples, you would get them much better than just keep telling them, okay, Newton's third law, there is a cart and there is a horse and horse pulls the cart pulls the horse. In fact, I've never understood what that is. Whereas it's much easier when you explain that there is the PSLV rocket standing there, and then once the jets start firing, why did the rest of the thing took off? And because all of them have seen on the TV screen, including today, how beautifully it rises in the sky against the forces of gravity. So therefore, I thought this kind of learning is important. Chandrayaan, of course, is very dear to us because right from very, very young days, my mother, for that matter, anybody's mother, used to use the moon and teach you some things, maybe may not be STEM particularly, but the foundations of that. And therefore, that is very appropriate that we take Chandrayaan 3 mission, which has become such a ray all over wherever I go. They want to ask questions about it. We'll come back to all that. And the question which keeps coming up is, when you look at moon as our nearest neighbor, there is obviously one of the outer space missions has to be to this planet, which happened during the 60s, for example. Then there was such a Cold War and the raised the USSR and United States, and then finally Armstrong landing there and so on. It was very much of a thing like that. But after that, people were wondering why there are not many more moon missions. But then in the last couple of years, or maybe a decade or more, there is definitely renewed interest in going to the moon. Why? Previously, it was more out of curiosity or showing off that, yes, we can also have a rocket which will take you all the way to the moon, land people, bring them back safely and so on. But now we look at moon as a possible source for our resources, because commercial space era is now explosively growing, as you would have seen the rate at which even one company, how Elon Musk's company, SpaceX, launches almost every week, and in one launch they have dozens of satellites and so on. So therefore, this is no longer the kind of once in a year or once in 2 years kind of activity. And therefore, it is not at all inconceivable that there can be huge habitats which can be built in moon, for example. But then, one of the main things is that to sustain the human life there, if moving the people is one aspect of that, and even if that is feasible, making them stay there would require their basic necessities of water, oxygen, and whatever, food and shelter and so on. And in that context, I believe one of the very important things which happened was the discovery of water attributable to one of the payloads of Chandrayaan 1, it was in the year 2008. And at that time, we also have one impact probe which landed in that region and confirmed that there is definitely hydroxyl ions and very strong indications of water, maybe frozen water underneath and so on. This was then confirmed by many imaging missions, and therefore the regions where we would like to explore essentially got shrunk. I have put 3%. Again, because my whole idea on this is to keep telling you mathematics and physics and other concepts. For example, the steradian, 4 pi steradian is the total solid angle of a sphere. Suppose I take, let's say, 70-degree latitude and below in the southern hemisphere, that is just 3% of the solid angle. And therefore, if you concentrate in that region, you have enough of excitement, enough of possibilities of getting the right resources to build habitats. That is why what I've shown on the top right is an Artemis mission, which is also coming up very shortly. It is a series of things where India also recently joined the international group. And Artemis is going to work very closely with us and make sure that the discoveries that we make from ours and they are exchanged, and then these are all building to something very interesting in the very near future. But then there are certain things which people do not understand. When you look at the Chandrayaan 3 mission, almost everyone keeps, there was a time when people used to be even asking questions like, what is this? If Luna 25 could be launched from Soviet Union much later and landing earlier than us, what is the kind of technology that we have? It was a age-old technology and so on, not realizing that these are all driven by very, very, very simple physics concepts. If you understood that, there is nothing, you can very easily compare them. For example, in just now I said that we are interested in the South Polar region, and within that region, based on the imageries that we have obtained through Chandrayaan 2 orbiter, we had figured out a small area, 4 kilometer by 4 kilometer, which looked flat enough, which looked like very interesting in terms of as a good sample of what needs to be done for the people who are going to explore that. That is basically the scientists. Because in ISRO, always, right from the very beginning, Vikram Sarabhai was very clear that if at all we do any missions like that, it should be driven by the user groups. In this case, it's the science users, and it is they who will decide what is to be done. It's not for the heck of it that you want to go there, have landed in the pole, somebody say polar region, let's say, and then say that, yes, I can put my collar up. It's not the way India would do the space program. And therefore, based on the interest shown by the research people, gathered through the Indian Academy of Sciences and later other groups, we selected that and decided on a spot. But once you get a spot there, when you want to go and land there, you have to fix the muhurt, the right time at which you can reach there. What are the considerations here? When you want to do that, you want to run it as much as possible using solar radiation, so that you do not have to encounter darkness and the kind of, because the moon is having, if you think of a day and night together, it's about 1 month. So about 14 days, it is going to be sunlit in any given part of the moon, and next 14 days it is dark. And therefore, if you could start at the dawn, at the site of our interest, we can go up to dusk, which will get us 14 days of good observations without a break. So this was one of the considerations. And this landing site, which we have selected, was having, let's say, July, August 21st to be the date on which that was where the sun was rising. But then it has to, because it's very much in the South Polar region, so therefore the sun doesn't get to right overhead, and therefore it rises slowly on the northern sky, and by the 2 days later it comes to 6-degree elevation, which is good. So therefore that was the next consideration. It has to be on that particular day. But then next question is, how do you land something safely, soft land at this location? Even if sunlight is, that way sunlight is not so important. Sunlight is required for the operation. But when you want to land it, you must have a way by which you have to slow it down, not only in terms of the uh, vertical speeds, which will be because of the lunar gravitational pull, but also because it has been orbiting. So it has got a lot of horizontal velocity, which has to be decreased. So all these have to be correctly planned in a guided system. So how do you think of that? Is something which we had worked out, and we knew that can be done from 30-kilometer kind of altitude. I'm going to go into some details, and then that can reach there, provided it was in an orbit of a very specific type. An orbit is given in terms of 6 parameters: the size and shape of the orbit, that is the semi-major axis eccentricity, then its orientation, and then in terms of within that, where is the perigee, and how far away from the perigee at this time it is. For example, today's mission, for those of you, it's more of a sharing in the small group of general knowledge. Today, the PSLV had a very different launch schedule, because we did not want to drop off Aditya L1. Usually what we do, we go from Sriharikota and go down somewhere. When you hit the region like Indonesia, near Biak and all that, at that point of time, give sufficient speed and then leave it there. You get an elliptical orbit. This is what we normally do. But then here, that will be a descending node. That means from the equator, will be going down, and that will be the perigee, because we inject it in. The orbit is decided by a second order ordinary differential equation, a second order vector differential equation for the position. So it requires two initial conditions: initial position, initial velocity. So the initial velocity and initial position together will be called injection parameters, and the injection parameters will be such that it will be dropped off at the perigee with the speed of 10.8 or whatever, less than the escape speed, you launch it. But today, Aditya, we had a constraint that the final orbit which you want to get should be of a certain nature with respect to the sun, with respect to the L1 point, a halo orbit. And that decides where you have to inject this, and that happened to be very close to the ascending node. After descending node, ascending node is half a portion of the orbit. So it was taking almost like 40 minutes, 45 minutes to go over to the ascending node area. And that is when the fourth stage was restarted, and finally it separated Aditya. So this is having got up to the capture, we go one step backward to get it into what is called the departure. Departure orbit means now when it was earthbound, when you launch it, you are in some elliptical orbit. Elliptical orbits are given by the perigee and apogee, and successively increasing the velocity at the perigee, you can go further and further away. You can make the apogee go to further distances. You understand? The kinetic energy is increased here at the perigee, because perigee point, the potential energy is whatever is the value. So total energy will increase. So the only way this gets compensated is going to a farther out point. And that is what is the main way of increasing it. We do it in multiple steps, not so much because we don't have the capability. We do it because when we want to burn, we should do it for as short a time as possible to get the advantage of nearly impulsive burn. Otherwise, there will be an arc over which it will burn. So there will be an arc loss, no? So that cos theta component you'll have to account for. So therefore, we did 4 or 5 maneuvers we can do. And because luckily our motor thrusters are all liquid propellants, and they can be restarted anytime you want. But what is the final orbit what you want to do, which was done on the 31st of 5 days before that, on 31st July, 8:54. That burn was taking you with a velocity which was still within the less than the escape velocity. It was not in a trajectory on the Earth. It was an ellipse only, but the ellipse was going with an apogee which was so high, more than the moon's distance. The values are given in your table, you can see that. And it is going beyond, but when it goes near the apogee, it moves very slowly. When it moves so slowly, what will happen? There is now the geometry there, what I showed, the capture geometry, that is what you have to ensure. So it has to come there. See, normally it's a two-body problem with the Earth alone. Here, when it comes to Earth and Moon, three-body problems are involved. But essentially, as it is moving around, you come to a region where the Moon's influence is the most predominant. So again, treat it as a two-body problem. And then you end up, the actual velocity which is there is that of a trajectory, of a hyperbolic trajectory, which is what you want to capture as soon as it turns around the Moon. And that part of it is done with a very detailed calculation of how much firing. And so look at the time. If we had not done the capture, it would have come back in another 4.5 days. It would have come back to the perigee because it will be in an elliptical path around the Earth. This is the basic thing. And this is, of course, giving you the details also. I told you the final orbit had 10.847 kilometer per second. That kind of the velocity of perigee, which is less than the escape velocity. Escape velocity on the surface of the Earth is around 11.2, but at these altitudes, whatever perigee heights, it will be around 11 kilometer per second. It's less than that. And so it's the elliptical path like that, and which did everything what we have already explained. Now let's get to shift the date into August 23rd, where we now have already reduced the size of the lunar orbit to 100 kilometer by 100 kilometer, and finally 100 by 30. And the 100 by 30 is done in such a way that the 30 kilometer occurs exactly over the starting point which we have already identified. Because that starting point must be such that if you look at the geometry of how this has to be slowed down, because it takes a finite amount of time to slow down the orbital speed, because it has about 1,650 meters per second velocity, so that has to be stopped. But you can't just stop it. It is like a plane when it's coming in. It has come close to Bangalore airport, about 3-4 kilometers away. He will not shut it down there. Oh, Bangalore, then if he shuts it down, then it will fall down somewhere. So he'll slow it down and approach our runway. Same way here also, the horizontal velocity will be slowed down, approaching the target. But then the vertical velocity is controlled by, initially there is no vertical velocity at all. And that part of it is going to be adjusted by again firing the thrusters, same set of thrusters for both, which is an extremely interesting problem of guided navigation, because it uses all gyros, accelerometers, etc., which are inertia. It is not, we cannot use a sensor which is based on planetary systems, star sensor or sun sensor. Earth sensor won't work. And it has got very interesting things, including velocity meters and so on. It's extremely new and all indigenously done. Well, you have all seen a lot about Chandrayaan 3, the lander and rover together, and what kind of specifications have been there. And the rover is very interesting, because I'm going to show a couple of images and so on, and then leave it open for you to ask questions. It had a number of payloads, just like today's mission also. Aditya's mission is not just taking it there 4 months it takes to go to L1, but then from then on, the wealth of information it will start giving is enormous. Not for us only, for anybody and everybody, and not only for scientists. It may be for meteorologists, it may be for communication engineers, for everybody. This kind of data will be useful to know about the solar activities. But coming back to Chandrayaan, so you have a Langmuir probe, which is measuring the electron and ion concentrations. Then you have a surface thermophysical experiment. I'm going to show you some results and other similar things. So now when you look at the results, of course, this is the how the solar sunrise and sunset at the chosen point at Shiv Shakti, and how it illuminates the solar cells on the lander as well as the rover. That kind of a thing. It's not so important here, but let me show. This is what I took today, and tomorrow's paper, I am giving it today itself for you. Tomorrow, everywhere, or today evening, this is the picture which will keep on coming. And this is something where in cricket we may not have got 100, I don't know the score now, but Pragyan has already made 100 meters and continuing. So in the first phase of the first lunar day of maybe 10 days or something, it has made right from the Vikram lander, moved westward and reached the point which I have shown there. And every one of these is a tremendous amount of coordinated activity. The kind of people whom I saw today and interacted with for about almost 1 hour involved people from control system, mechanisms, from image processing guys, from the payload interpreting guys, and then you have the extract people, and then the command generation, mission plan. All of them work in cohesion. And because this decision of how it moves is not made by autonomous logic, it's made by ground personnel. So therefore, you command it to do any movement or turning everything. That's why you saw one of those days. It in fact made a projection. It was going around itself 360 degrees almost, because it has to turn around and come back because there is a crater which was coming very close by. And some of these are amazing, because I saw with a resolution which is about 1000 times what you see here, and then you know what features are there and how complicated it will be to drive through this path. Another thing, which of course this is the Langmuir probe, where it shows the electron and ion current. So the expected ones, but the values are important for scientific community. But as people who are physics people, as I am absolutely thrilled by looking at this observation, which all of you would have seen, that when you have measured the temperature as you go down, let's say 8 centimeters kind of thing, is not a big difference. But how much the temperature has dropped, almost 70 degrees or so across that short distance. So it's about 1.5 degree per millimeter, which is going to be extremely important to be able to generate electricity using what you would have studied in PSC classes, Seebeck effect. Peltier and Seebeck. Seebeck is the way, but when two dissimilar metals are joined together forming thermocouple junctions, and if the two are kept at two different temperatures, there is a voltage which comes up. And this is a tremendous new discovery, in my opinion, because everybody knows this as a principle. But if this is the kind of difference in temperature, and this is maintained with a large reservoir, it doesn't get equated just because it's just such a short distance. You can go far deeper and get even larger temperature differences and be able to generate electricity in a way which is quite different from other ways people depend only on solar. And especially in South Polar region, there are regions where they are in permanent shadow. There's no solar thing, but you can use this for generating electricity. I was very excited. And several things like this discovery of the materials. Just about 10 days back only this gone there, and the wealth of information and how much time it's going to take, how many PhDs it will produce, how many papers will be published is going to be countless, because all these are being done for the first time. With this, like sulfur being discovered here, is going to open out a lot of new ideas for a variety of purposes. Of course, during the very beginning, the reason why I got into this STEM was I was trying to sort of answer to some of the students whom I was addressing, what kind of questions was repeatedly coming up, and I wrote up the answers and circulated. And that became popular. That's why they wanted me to give a talk on that. All these are very standard kind of questions, and many of them are not really, like I was talking about lunar 25. If it had landed, unfortunately it had a failure, but if it had landed, people would have been all the time saying that, yes, you did a fantastic Chandrayaan 3, but Russia did it much shorter. Why can't you do? Like they would have been asking. Whereas it was all policy decisions, which are fully known decisions, based not on technology, but on some things which are very well established. And we wanted that kind of time and cost reduction. So, yeah, look at this, for example, because hyperbolic arrival trajectory, how it was captured. When you look at this, you'll see if it had continued as hyperbola, it would have been that particular blue kind of line. If you had not done the maneuver, lunar capture maneuver, it would have just gone off from the moon and gone out. But now, because of this maneuver done at the exact point, we converted it into an ellipse. So that's why it's going round, round, round like that. And then we made it smaller by doing more maneuvers and finally made it 100 kilometers circular. So I think that's what I thought should be good to keep at least 10 minutes of discussions. And at the top, you see the very often projected earth-bound maneuvers and the lunar-bound maneuvers, and connected by the lunar transfer trajectory. Thank you.
I'm looking into the newspapers, and I don't know whether that is factual correct or not.
Yeah.
They are saying like the rover has only lifespan until September 3rd, and then it has to return back to the docking station. Is that true, or a rover has more lifespan? Because I do see the solar panels and battery packs and everything.
See, two things. The solar panel is there, battery is also there, but the battery is not having enough storage capacity for making it work through those 14 days of continuous non-illumination. Okay, so therefore, what happens? We designed it so that in the first 10 days you would have done this 100 meters of movement, and then it has studied various in situ observations have been conducted. By no means anybody has ruled out the possibility of using the lander as well as rover into the next cycle. So this may end by September 3rd, that is tomorrow, late evening or something like that. The sun elevation is already coming to 5 degrees or so. And the next day it might even come down to 1.5 degree and then set. And therefore there will be no power generation, but nothing ever goes off except the fact that the electronics are generally expected to work from minus 10 degrees to plus 50, like that only we qualify. Here, the temperatures, when it is night time, that lunar night, goes down to around 200, 210 negative, minus 210 degrees centigrade. So at such cold temperatures, if some wiring, something comes off, then it may become non-functional. So what we have done is today, at the end of this operation, I was also present there, we have oriented the rover in such a way that it is optimal for its solar panel to get the maximum solar radiation as soon as the sun rises again. And once the power comes up, then the communication will be there. Till that time, we will not be able to get a communication from these units, because that is rovers. Rover communicates to the lander, but the rover communication will not be possible when it's not having power. So therefore, we, in all probability, will expect one or more of these cycles of 14 days, which will happen if, while mission was planned, it was planned for just only this. It's nothing gets shut down. It's going to be left there, and it can come back to life. Yeah.
Sir, in the speech you mentioned scientists decide what topic they want to explore, and this time they wanted to explore
these materials and so on. Yeah.
Exactly. So I am curious, in general, what basis India scientists are focusing in positioning India in terms of space exploration? Is there a strategy?
Because if you look at tomorrow's paper, there will be a big list of what are all the payloads on Aditya L1. See, that the way it's contributed by Indian Institute of Astrophysics or by PRL or by a host of other agencies, all those things finally feed into the mission. We always have done that. Like one of the very famed one is AstroSat, no? It made fantastic imagery, lots of publications. In that satellite, the information window, he was also another friend of mine, TIFR friend, who was the person who designed the payload. And the platform, everything was designed by my other friends in ISRO. It was such a fantastic mission, which everybody talks about it, AstroSat, which was about 10 years old.
So I think there must be a clear roadmap. I think Prime Minister mentioned it. And
now, with the successes, I'm sure this will happen even more. See, there was a time when we always used to do, when we were all in the very beginning, about 50 years ago, ISRO had this thing that I was in charge of the INSAT program. It had payloads which have to come for communication, broadcasting, meteorology, everything. All those government agencies will come and gather in one big room, Vikram Hall in Ahmedabad. We will go there and we'll take notes. I want this channel with this resolution. It should be with this bit. All these will translate it to a proper payload specifications. That is how the whole thing starts. Same thing with remote sensing. How all those different kinds of, because remote sensing products, how will they use? It cannot be decided by the space agency. So therefore, what resolution is required, which band is required, all are coming from users. Same thing here also.
I had read that this Chinese mission, Chang'e 5, their rover had scooped something like 1.7 kilograms of soil
Yeah.
And in that sample return, they had found a mineral called changasite. Of course, they have named it as changasite, which is supposed to be a big candidate for possibly mining the lunar surface by future missions, because it contains helium-3 and things like that.
Yeah.
So
Yeah.
can you throw some light on that changasite? I mean,
Sure.
as a geologist,
Yeah.
makes me
Certainly.
interested.
First and foremost, yes, helium-3. Just now, even to the other question, we talked about power issues and all that. Helium-3 availability will make things so good. If sample return can get helium-3 returned to the Earth, it's going to make a lot of difference in terms of generating nuclear fusion power kind of things in India. So, but now, in terms of the finding of availability of helium-3, the regions which China has explored are different. In fact, they have tried mostly on the far side, the non-visible side of the moon. They have had landings and they've explored 2-3 good regions, but they've not come down in latitude all the way down to 70 and below and all that, and 70 and above. So, and therefore, the regions where they have explored have probably got more of helium-3, but today it's only a guess, because with 2 or 3 samples, we cannot extrapolate. So therefore, I think Artemis is seriously looking at sampling it at different places. Like here, we used to put the geode phones and all that, not different places, and collect data. Same way, it may be possible that you collect samples from different parts and first classify that geology or equivalent word for that, and then be able to see why there should be a different kind of composition in different parts. So that is where the theory and experiment will help. If you find some new materials, altogether new elements or new compounds, then that will give some clues to the evolution of the entire thing in the solar system in the pristine, pure state. And that probably will throw some light.